Okay, so here we go. So in the last class, we started the kind of discussion of the Landau-Ginzburg model, although actually we did not start the Landau-Ginzburg model, but uh, kind of preparing background for the Landau-Ginzburg model. And one of the things that we were looking at was the liquid gas phase transition, or in fact, what we were looking at was the phase diagram of solid, liquid, and gas system. And what we said was that one sees a critical point in the um, line separating the liquid and gas phase, which on one side ends on a triple point and the other side it ends on a critical point. And the line separating the solid state from gaseous or the liquid state does not end anywhere. That is first observation. And the second thing was the reason why we wanted to study this system was that liquid gas phase transition falls in the same universality class as the Ising model. So the point that I wanted to make here, particularly when one is studying systems in the neighborhood of critical point, is that it is not necessary that the system uh, has to be a lattice model, or the system has necessarily should have only degrees of freedom which can take discrete values. Uh, it is not essential. In fact, liquid gas phase transition system actually contains continuous degrees of freedom to use quantities like density or volume or pressure as variables, and those can be varied continuously in the system, as against the Ising model case where you can have spins which can take plus or minus one value. Okay, so the universality class concept is much wider than what any specific model could actually tell you, and the universality class concept is only sensible when you are in the neighborhood of a critical point. That a large class of disparate looking models would have similar critical behavior. Okay, as you go away from the critical point, then more detailed information about the models may start becoming important. Mm, And however, if you want to study these models in the uh, in some kind of perturbative fashion, in the sense that like study universal behavior of the system near the critical point, but if you are away from the critical point, you want to study the deviation from the critical point perturbatively, then in fact all these models would behave in the same fashion. Okay, so liquid gas system would behave quite differently if you do not treat it in a perturbative fashion around the critical point. But if you do treat it in the perturbative fashion, then liquid gas system, binary alloy system, Ising model, and there's a host of such class of models which all belong to what's called the Ising model universality class. Okay, so the purpose of getting into the liquid gas transition discussion was to say that when we are going to talk about Landau-Ginzburg type model, it is not that proposer is not pinning its hopes on a specific model. For example, it is not kind of you know deriving its intuition only from say Ising model with a square lattice, and at every lattice point you have only up spin or down spin kind of configuration. It is much more of a broad brush picture, which is supposed to uh, kind of cover large class of model with similar or identical critical behavior. Okay. Although we would be using model universality class as an example while studying the Landau-Ginzburg model. Landau-Ginzburg model have validity which is much wider than that, in fact. Okay. So, but to treat other universality classes would become much more complicated thing to study, and it clearly is not a one semester long course. In fact, if you want to study, say, Potts model kind of universality class, for example, you'll have to kind of formalism would be identical, but detailed results would of course vary, and you need to compute them separately. Okay, but Landau-Ginzburg model, concept of Landau-Ginzburg model is not to actually do tell you about how the details differ between different universality class, but to write down a formalism which can be used for any kind of universality class. Okay, in that sense, it's a very broad-based formalism which can be applied to a large class of systems. Okay. Now, of course, if you want to give a description which is so broad-based, it of course has to do a lot of, you know, shove a lot of things under the rug and kind of, focus on the quantities which are important for giving the description of the system near a critical point. Okay. So one of the important things which was critical for the Landau-Ginzburg proposal was this argument of Landau that the lines separating these transitions uh, are because the phases across the lines have different symmetries. And if the symmetries are different, then there shouldn't be a path which would continuously connect one to the other. Okay, and this was one of the reasons why he wanted to set up a model which would try to preserve the symmetries of the microscopic model that you would want to study, say, Ising model or say liquid gas phase transition, and um, preserve those symmetries in a broader picture and try to see whether one can understand the system better. Okay, fine. So, so we looked at this PT phase diagram, and uh, you know, we understood as to, if you are sitting at one point which corresponds to both P and T fixed, and if you and with the coexistence point, you are essentially doing a transition from gaseous state to liquid state. The volume of that system has to change if the densities of gaseous and liquid states are different. So in the coexistence phase, you would see large coexistence phase depending upon what's the temperature below critical point and temperature that you are trying to study the system. That is the point of this particular graph. Okay. So yeah, so maybe I can skip this part. We had already done this discussion. And so, but main point that led to understanding of these phase diagrams, the one which I had drawn earlier, not this one, but the one earlier, uh, was completely based on Landau's kind of observation that one should kind of worry about how the symmetry structure of these systems uh, across these lines differ. Okay, and so based on that, one basically tries to ask what happens on the coexistence line about thermodynamic quantities, and if you get multiple relations, then you should therefore find that multiple relations to be valid on the spaces of higher codimensions. By codimension, I mean if you are looking at a d-dimensional space, and if you put one condition, then that condition will be satisfied on a d minus one dimensional surface. For example, if you take x, y, z three-dimensional space, and if you say x squared plus y squared plus z squared is equal to 1, then that object is two-dimensional surface, which is the surface of the sphere or surface of a football, which is two-dimensional simply because it is parameterized by two coordinates, theta and phi. If I tell you theta phi value, you know the point on the sphere. Okay, so you would say that sphere is codimension one space in three-dimensional space. But if you impose two conditions, then you can easily see that two conditions will be satisfied only on a line which would be a codimension two spaces. So this is what happens here, that if you get a single condition for the chemical potential, then that is a single relation between P and T, and from the P and T graph, this one condition on two parameters should give you a line. Okay, whereas if you get three conditions corresponding to liquid, solid, liquid, gas chemical potentials, then because of the two conditions, generically you will only get solution for finite number of points. And this particular case, you really get only one point, which is the critical point of the model. Okay. Uh, Critical point also has a similar condition. You have chemical potentials and the volume agree, and that kind of follows from this PV diagram that we looked at. That if you are at T equals Tc, then you actually have a tangential touch to the coexistence line, and therefore the volume of the gaseous state and the liquid state actually does not change when you undergo this transition. Okay, so that is why you get this second condition, that V1 is equal to V2 at the transition point, and therefore you get only a single point as a solution. Okay, so let's kind of get to kind of formulating the Landau-Ginzburg theory. And that is, in some sense, a next level of sophistication after mean field theory. Although, as we will see, that Landau-Ginzburg model at the lowest order, or at the most coarse-grained order, would essentially reproduce mean field theory for us. But nevertheless, Landau-Ginzburg theory has much higher value than mean field theory, because the whole concept is derived from the Lagrangian formulation of the theory. Okay. The approach is, of course, completely phenomenological in the sense that that you look at the systems, or look at the models that have been studied, and based on those models, you decide as to which aspects of those models are physically important in setting up the Lagrangian formulation, and then you discard various other kind of frivolous, okay, I shouldn't use the word frivolous, but various other details of the model which may not have important consequence when one tries to study the critical behavior of the system. Okay, so that is the place where actually the great insight of Landau and Ginzburg gets into this setup, and that is the reason why it is one of the defining kind of formalism for studying critical phenomena. Okay, of course, the newer models have done much better, and we will of course look at those, like Wilsonian renormalization group technique, which will be part of the course. But before that, we should at least appreciate how Landau-Ginzburg have kind of set up the system. Okay, so first thing that we will do is the following, that we will do some small changes in the notation. Okay, and the reason for that is exactly what I explained just a few minutes ago, that Landau-Ginzburg wants to give a general setup. They don't want to say that, okay, look at the Ising model. There's an order parameter which is magnetization. Let me write everything in terms of this magnetization as an order parameter and a system based on that. Then I look at liquid gas system, I write down density as order parameter, and then try studying that. They don't want to do that. They just want to say that, like, the system would have some order below Tc. So there has to be an order parameter whose value is non-zero in the ordered state, 0 in the disordered state, and these two states are separated by the critical point, and that is a place where the order parameter would take off from its 0 value to some non-zero value in the ordered state. Okay, so let's define that order parameter as phi of x. Okay, this would be magnetization if you talk about Ising model, density if you talk about something or other. Okay, that is the thing. Okay, now if you recall, magnetization, although spin in the Ising model took plus or minus 1 value, magnetization was almost kind of a continuous variable. It would be 0 at T is equal to Tc. Okay, it will continue to be 0 for all temperatures larger than Tc, but it will kind of gradually rise from T equals Tc to lower temperatures. Okay, and therefore it would make sense to think of magnetization as a continuous variable. Okay, and therefore Landau-Ginzburg propose that the order parameter phi that they are going to look at is actually a continuous field. Okay, so so in some sense, this is what one calls the coarse graining of the microscopic degrees of freedom. You don't look at the spin degrees of freedom or the, say, binary alloy, two different material systems, or liquid or gas degrees of freedom, but you just write down a continuous field. Okay, so so as I said, it will be, magnetization in one, it will be density in another. Okay. Now, one important thing that we should remember here is that, like, this procedure involves coarse graining at two different places. Okay, and these two coarse grainings are the following. First thing is that our models are typically defined as lattice models. Okay, like Ising model was defined on a lattice. Uh, Say binary alloys, copper zinc alloy model also would have been defined on a lattice. They are naturally cubic lattice kind of systems. Okay, liquid gas phase transition is not a lattice model, but this is, uh, I mean, the typical set of models are kind of lattice systems. So what you're doing is that first class of coarse graining that we are doing is we are treating x as a continuous variable. Okay, so far we were studying x as some uh, m comma n kind of, m is a lattice site, mth lattice site along x-axis, n was a nth lattice site along y-axis, and stuff like that. But now we are going to treat that as a continuous variable. That is first thing. And second thing is, as I said, that magnetization is for a spin up-down system would, although would be continuous, but it won't. If you study it microscopically, it's not exactly a continuous variable, but you treat that also as a continuous variable. So there are two versions of coarse graining that is involved here. Okay, so this is so remember, like, the expectation value of phi of x is magnetization. And if you try to recall, the magnetization in the spin system was defined as the expectation value of the spin degree of freedom summed over, of course, all the lattice sites is was the effective magnetization of the system that was written down. Okay, so in other words, the spin degree of freedom, which was taking plus or minus one value, is actually replaced by a continuous field. Okay, so as you can clearly see, it's kind of a large amount of coarse graining, but the whole idea of coarse graining here was to show that eventually it will have exactly the same class of solutions, or what one would want to call vacua, as the Ising model would. Okay, so vacua is, of course, a quantum field theoretic kind of terminology. If you study statistical models, then you wouldn't use the words like vacua, you would call them ground states. Okay, but they are one and the same thing. Okay, now if you look at Ising model, say in higher dimensions, say two-dimensional, three-dimensional Ising model, then we know that it has phase transition, and and for temperature T less than Tc, the preferred ground states are the ones where either all spins are pointing up or all spins are pointing down. So that would tell you that, like, the ground state is in some sense twofold degenerate. Okay, we will have to see whether a model that we would write down involving phi of x, which is a coarse-grained variable, say for the Ising model, whether it also produces the results of similar kind. Okay, so of course, the whole Landowner proposal was based on the fact that it would do that, and we will see how it happens. Okay. Now recall that in mean field theory, we some typo. We get the magnetization to be something like this. Okay, tan hyperbolic h by kbt plus m times tc by t. Okay, and in the absence of external magnetic field, what we get is an expression which is like this: some number times m plus some other number times m cube plus some higher powers. So they are just expansions that we are trying to do. Okay, and of the tan hyperbolic, and you just take this m on the left hand side and set that expression equal to 0. Okay, where this coefficient a, if you do this expansion, you will find that that is some number times t minus tc. Okay, so that is the expression. Of course, this expression this expansion would make sense only if you have in the neighborhood of t equals tc, because that is the point. In the neighborhood of t equals tc, you have small magnetization, and in that case, expanding tan hyperbolic would make sense, because you set h is equal to 0, this term goes away. Tan hyperbolic with a small argument takes small value. Okay, so therefore it would make sense to do this expansion only if t is in the neighborhood of tc. Okay, so what we will do is that we will ignore the ellipses, dot 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 pieces, and just ask that if you have an equation like this, then how would you obtain that as extremization of some function? Okay, and it's kind of obvious that if you have something like this, then it is extremization of a function like this. You take this as a function, say call it f, then del f by del m would produce this expression. Okay, derivative of this will get rid of this factor of 2, derivative of this will get rid of this factor of 4, and you get a linear term and a cubic term. Okay, so you would say that if this was the conditions for magnetization, then this being treated as an extremization condition would follow from a function which is defined this way. Okay, fine. So what we are going to do is that in the Landau-Ginzburg model, we are going to treat this function as the potential energy term. Okay, such that when you write down variation of the Hamiltonian or the action functional, then variation of the potential would produce a term of this kind. Okay, so that is the idea. Okay, now of course we want to express this m as the expectation value of the order parameter phi. Okay, but of course, in the spin system we have defined m to be expectation value of the spin degrees of freedom. Okay, so this would tell us that this expression, if I want to write down a potential energy term in the Landau-Ginzburg model, which is a model written in which the dynamical variable is the order parameter, I should be writing down the potential energy term, which is a by 2 times phi squared plus g by 4 times phi to the 4. Okay, so that is what would be the quantity which will be sitting around here. Okay, so I just want to kind of step back a little and kind of draw your attention to something that I stated here, that the coefficient a is takes the value t minus tc when you do an expansion of this type with some numbers sitting around here. Okay, and if you forget about the quartic piece, and if you add a kinetic term to this, okay, say to this problem, then you would in the Fourier mode, if you look at its behavior in the momentum space, then you would get the term which is k squared phi squared plus a. Okay, maybe I should say this way: k squared by 2 phi squared plus a by 2 phi squared to be the quadratic part of the action. Okay, and the reason why I wanted to draw that attention is because that a by 2 times phi squared piece would have t minus tc dependence. Okay, the reason why I want to say this is because we encountered exactly same kind of behavior when we looked at the 2D Ising model. So let's just step back and just show that expression. If you recall, I was mentioning that k squared plus epsilon squared factor is precisely the quadratic piece of the term that you would want to write down. Okay. Did I go back too much? No. Okay, so here. Yeah, so you encounter expressions like k squared plus epsilon squared, and this epsilon squared is precisely the factor a that we are seeing in the quadratic part of the action, and that fellow has a t minus tc dependence. That dependence is something that we used in determining the behavior, second derivative of f with respect to epsilon gives you this quantity, and we interpreted that as CV by saying that epsilon is proportional to t minus tc. Okay, so that is the behavior that you would have seen even if you had looked at the Ising model setup. So in the Landau-Ginzburg setup, this kind of term naturally occurs as a mass term in the potential energy expression. Okay, any term which is quadratic is would be proportional to the mass term. Okay, fine. So another important thing that you will notice is that if you are above above the temperature Tc, okay, so T minus Tc is positive, then in that case A is positive, okay, and therefore you get a positive m squared plus positive m to the 4 pieces. Okay, we are assuming that G is positive. Okay, but when T is less than Tc, then A is negative, and therefore it is the quantity which is minus m squared plus m to the 4. Okay, and therefore the system has two different types of behavior as you go from T greater than Tc to T less than Tc, and that is precisely what the Landau-Ginzburg actually exploit in this model. Okay, as we'll go ahead, we will see how that happens. Okay, probably not today, but maybe in the next class. Okay, so the potential energy functional for the order parameter takes a form like this, with A having a linear T minus Tc dependence. Okay, fine.
Sir?
Now, yes.
Can you go back to this expression of this polynomial? So
Yes.
this AM plus GMQ, this expression being 0, this in the mean field theory, this was valid only in like when the temperature was less than Tc.
That is
and
right.
they're getting to 3 different solutions.
Yes. Yes.
But
but it is true even for T greater than Tc because the only valid solution would be T m is equal to 0. The other solution is complex.
Okay. Yeah. I mean, what I'm trying to ask is can we always can we always assume that the parameters that we are using to write the theory, they are themselves analytic?
Well,
in terms of temperature.
In terms of temperatures, sorry, is that the question?
Yeah.
Yeah. Well, the point is that like the system is has analytic behavior for most of the temperatures. Okay, and that's the reason why we assume that all these variables are analytic functions of temperature. Okay, so if you experimentally observe the system, you find that there is no non-analyticity in the system for most of the temperatures. Okay, this is exactly that convex function kind of argument, that the function is analytic almost everywhere except for a few points where it may have non-analytic behavior, and that behavior, that experimental observation is the one which forces us to kind of write down models which have analytic dependence on thermodynamic variables like temperature or pressure or something, depending upon what is the setup that you are looking at. Okay, and but our interest is in finding out under what circumstances the system develops non-analytic behavior. So input is analytic, output is non-analytic. Okay, and that is the thing that we want to pick up actually.
Okay. Yeah.
So critical phenomena is precisely this point, that everything that you have written down is analytic, and in spite of that you get answers which are non-analytic. Okay, and that must be something very universal about the system. Okay.
Yeah.
Okay. So here's the other aspect of the coarse graining, that in the spin system, the Hamiltonian was written in terms of the spin degrees of freedom, which would take uh, which will take kind of plus or minus 1 values. And uh, what we will do is we will replace this discrete degree of freedom by a continuous field. Okay, and in this particular case, in fact, phi will be treated as a real field, and therefore it will take all real values. Okay, so we have not only kind of replaced the discrete values of the spin, but we have actually liberated it to take all real values. Okay, so so that is another coarse graining that one does. Okay, so so there are so so as I said, like there are two limits that we want to take in the Hamiltonian. One is of course this, that you replace discrete variable by continuous, and the second thing is of course you take continuum limit of the lattice. That means you take the lattice spacing going to 0 at some point. Okay. This is very unfortunate that I used A here as well as A here. This A and this that A I have nothing to do with each other. Maybe I should change, call this some other variable. Suddenly realized. Okay, so let's try to figure out how we would do this. Okay, so what we will do is we'll kind of go back to the spins Hamiltonian, and we know that this Hamiltonian can be written in this particular form. Okay, so there is a, you can write down this as uh, si squared plus hj squared minus si minus hj whole squared. The square pieces will cancel out, and the cross term is the one which survives. Okay. Now, what we will do is we will replace these si's by phi's. Okay, and the ij variables by x's. Okay. So what we will do is that we will take j as a variable for which we will write x. I is a variable which is nearest neighbor. We'll call it x plus the lattice vector. Okay. So this expression written in this particular form can be written as phi squared at x plus a plus phi squared at x minus phi at x plus a minus phi at x whole squared. Okay. So now you can see that the last term, when you take the continuum limit, is going to look like the derivative. Okay, so it's going to look like a squared times the gradient of phi whole squared. Okay, so this is a term which actually produces the kinetic term for the order parameter. Okay, so in other words, if you want to vary the field phi, okay, then it is going to cost you some energy. Okay, and that energy cost is what is this kinetic energy piece that you would pick up from here. Okay, so what Landau Ginsburg would do is that they would claim that the critical behavior of the system is picked up by this potential energy functional. But remember, in the mean field theory approximation, we always said that the order parameter took constant values. Okay, and only for constant order parameter, by constant means spatially constant. It does depend on other thermodynamic quantities like temperature and stuff like that, but does not depend on space. Okay, and when you choose that to be spatially uniform, then we determine the solutions in that, like m is equal to 0 and m is not equal to 0, depending upon whether you are whether t is greater than or t is less than tc, and we found out what is a spontaneous magnetization. Okay, but your order parameter could depend on space. Okay, if that is the case, then this is not the complete description of the story, and what you need to do is to actually incorporate the spatial variation of the order parameter, and that would give you a term of this kind. Okay, and clearly a spatial variation of order parameters would cost you some energy. Okay, if you think of it from the lattice model point of view, then if you want to kind of say that the spins take different values at different lattice sites, that would clearly would require higher energy, because spin taking different values at different lattice sites. I mean, like you may have spin taking same value of most of them, but at few lattice sites, if the spin flips, then nearest neighbor interactions would be enhanced, and therefore it will cost you some energy. Okay, But now we are trying to give that same stuff. This is described in terms of a continuous field, which we call phi, and the cost in energy is basically gradient of phi over space. Okay. Fine. So what we'll do is we'll put all these pieces together and we write down the energy functional, which is what's called the Landau-Ginzburg energy functional, and that takes the form of this type. Okay. We have replaced the summation by a d-dimensional integration. Okay. This is a piece which came from the JSI.Sj term. Of course, you would say that like what happened to the factors j and stuff like that. They can all be soaked up by just redefining the order parameter. Okay, so these factors are not that important. That would just require you to kind of redefining various I mean order parameter and various couplings. Okay, in fact, we will see later on that even the factor of beta that would be sitting around in the partition function also can be soaked up by redefining various quantities. Okay, fine. Now, of course, you know, this is not the correct, this should not be a complete description of the system, simply because when you take limits of this kind, you know, you not only get a term of this type, but you get also higher order terms. They will be proportional to higher powers of A, obviously, but those terms exist. And in principle, we should actually keep those terms in this Lagrangian or in this energy functional. Similarly, when you expand tan hyperbolic function, we had lots of other terms. There was m to the phi term uh, here and so on. Remember, tan hyperbolic is an odd function, and because it's an odd function, you don't get even powers of m in that expansion. You only get odd powers of n. But we chose not to look at those terms. Okay, so that's why our energy functional actually truncates to a form of this kind. Okay.
And what are we doing with the phi of x plus a plus phi of a term?
Oh, that is a factor which will also add up to. This is like a mass term, right?
Yeah,
Okay.
so it's absorbed
So
in the
yeah,
coefficient.
it's absorbed in this coefficient. Yeah. Okay. So what one gets basically is that the energy function would take a form of this type, and we want to study its behavior, its low energy behavior, because we are concentrating on how the ground state of this system is going to behave. Because magnetization is a statement about whether the ground state is magnetic or not. Okay. So therefore, for low energy physics, you can ignore higher derivative pieces which are higher orders in k, which would be higher powers in k, and which will be subleading. Similarly, we will ignore terms which are higher powers in phi, like phi to the 6, phi to the 8, and so on, because it's kind of, you know, saying it in a reverse order, but as we will see later, that these terms will play no role if d is greater than or equal to 3. Okay, so in some sense, critical behavior of the system is not affected by terms of this kind. Okay, so therefore you can happily ignore them for the time being. Okay, so of course you can compute the uh, correlation functions involving operators of this kind, but uh, if putting them in the energy functional does not determine the critical behavior of the system. Critical behavior of the system is independent of functions like this. Okay, fine. Now let's go back to the spin system again. And in the spin system, when we wrote down the partition function, we summed over all spin configurations. Okay, there was a sum over Si taking plus or minus value for all I. Okay, that is the partition function that we wrote down. But now what we are doing is we are replacing the Si by phi. Okay, so and SI was taking only plus or minus one value, but phi is taking continuous values from minus infinity to plus infinity. Okay, and therefore what we need to do is to replace sum over the spin values at all lattice sites by integral over all kinds of values that phi would take for all kinds of spatial values. Okay, so It's an integral which involves integral over values of phi for every x value and a integral over x. Okay, so that is the kind of integral that we need to do. Okay, fine. So therefore, our partition function that was written down in the uh, case of lattice model would take the form which is like this. Okay, so the sum over Si is replaced by uh, integral over various values of phi. Okay, and the e to the minus beta h factor that was written down will be written in terms of e to the minus s. Okay, where s is a quantity which is beta times the energy functional. Okay, the energy functional was just written upstairs here. Okay, I've just taken it from there and just written it down here. Okay, so our e to the minus beta h would be written in this particular form. Okay, so as I said, we would again rescale, various things. You can rescale coordinates, phi, a, g, everybody to soak up this beta appropriately. Okay, and what we'll do is we'll kind of forget about that at some point. Okay, fine. Now, this particular partition function takes the form of what's called an Euclidean path integral. Okay, so you may not have seen the Euclidean path integral uh, for quantum field theory because you are just studying the first part of you're studying QFT1 course. So what I'll do is I'll kind of do a quick recap of what is uh, the meaning of this statement. Okay, but you must have done path integral in quantum mechanics, right?
Yeah, it was.
It must have been done in QM2, right?
Yeah.
Okay, good. So I will not do the path integral in quantum mechanics because that is kind of something I'll assume that you know. So I'll just write down a few lines about it and continue. Okay, fine. So we will kind of come to this point about the path integral stuff soon. But before we do that, let's try to understand what are the features of this partition function. Okay, with this uh, action functional, if I may say so. Okay. So first thing is that that you could do is you can introduce the external magnetic field term, and that external magnetic field term would add a term linear in phi. Okay, and that is a term which is like this. Okay, because H coupled to Si, sum over Si, and sum over I Si is same as integral over the space times phi, because that is what is the proposed replacement by Landau and Ginsburg. Okay, so this naturally tells you something, that if you want to compute correlation functions involving the field phi, then all you have to do is to look at this expression. Suppose you have a s which is replaced by s minus h times integral of phi, then all you have to do is to differentiate this quantity with respect to h sufficient number of times to bring down phi, and just compute that correlation function. Okay, so that is the technique. Okay, fine. So let's kind of try to understand what are the features of this action functional. First thing is that it is local. Okay, by local I mean it is defined at the same lattice point. Same spatial point, and it involves only finite number of derivatives. In this particular case, it involves only one derivative. Okay, now you may have action defined at single point, but suppose instead of having a gradient acting on phi, suppose you have something like e to the gradient acting on phi. And that is not really a local theory, because e to the gradient acting on phi actually does a finite shift in the position of phi. Because remember, if you want to shift an operator, you act by derivative. But if you act by e to the derivative, then it does a finite shift. Okay, so such an operator is not local, but we are not doing anything like that. So this is only the first derivative, and therefore the entire action is local. Okay. Now this fact that it is local is partly due to the original model, in the sense that like the original model had nearest neighbor interaction. Okay, and that is why the model in the continuum limit would eventually reduce to local model. Okay, it's also partly because we ignored higher derivative terms. Okay, and we said that the higher derivative terms are small uh, compared to the say two derivative terms, and therefore we kind of ignored those. Now, of course, if you keep finite number of higher derivative terms, for example, grad phi to the fourth, okay, instead of grad phi squared, suppose you write down a grad phi to the fourth term. Now, that is not something which is going to occur by doing the approximation that we did just now, but suppose you do it by put it by hand. Or the other term which would actually appear in the expansion is grad squared phi whole squared. Okay, these are higher derivative terms. If you take finite number of those higher derivative terms, the theory is still local. Okay, so there is nothing to worry about, generating non-locality by adding a term or two. Okay, but if you have infinite number of terms sitting around, then the action is not local. Okay, but as we just argued that even if you work at not very, even if you work at momenta which are not very small, but you know, uh, reasonable value, but not very large, small but reasonable value, you may want to add grad square phi whole squared term to this action. Okay, uh, but uh, but that is just about it. You are not going to add like higher and higher derivatives because they would continue to be suppressed compared to the lower derivative terms. Okay, and therefore the action would continue to be local. Okay, fine. The second feature is that the action is spatially uniform. By that I mean that there is no explicit X dependence in the action. Okay, there is nothing like uh, like phi squared multiplied by some function v of x or f of x kind of object, and there is no explicit X dependence. There is an implicit X dependence in the field. Okay, but that every field theory has. Okay, so so in that sense, the action is spatially uniform. You could define it anywhere in the space. Okay, that is kind of we could associate with the fact that the original material that you looked at was uniform in space. Okay. The third aspect is something which is that it is polynomial in phi, and this is of course due to the coarse-graining procedure that we used, where we where we replaced si by the order parameter phi, and and while doing this transformation, we could have had terms which should have gone higher and higher powers in phi, like expanding tan hyperbolic function. Okay, but we we basically used, or maybe Landau Ginsburg basically used the fact that the physics that they are looking at in this particular system is not at the length scale of the lattice size. Okay, so lattice size may be of angstroms units. Uh, the total system may be of the order of few centimeters or few meters, and they are looking at the behavior of the system of the order of say, uh, you know, tens or hundreds of micrometer, which is like 4 or 5 orders of magnitude larger than the lattice size, but 4 or 5 orders of magnitude smaller than the total size of the system. Okay, and if you look at the systems of that kind, then you could ignore higher order corrections. Okay, and as a result, the action would be just polynomial in phi, whereas tan hyperbolic phi itself is not a polynomial function at all. Okay, so although it is an analytic function. Okay, uh, so yeah, so that is another thing which of course involves the insight that Landau and Ginsburg had, that they are studying the system where correlations would die out at distances which are much smaller than the total size of the system, but die out at distances much larger than the smallest unit of measurement of distances in the system. Okay. The next thing that we have in our model is that the action that we have written down, it preserves the symmetries of the original model. Now remember, the original model had a symmetry that if you set the external magnetic field to 0, then in the spin system, the Hamiltonian was invariant if you swap the spin values from whatever it was to minus of whatever, minus of that. Okay, SI going to minus SI. And that is simply because we had a term which was J SI times Sj with Ij are nearest neighbors. Okay. This corresponds to phi going to minus phi symmetry in the Landau-Gisberg action. And if you go back and look at the action, it is actually invariant under phi going to minus phi. Okay. So the important symmetry of the spin system is actually preserved by this action. Okay. In spite of replacing discrete degrees of freedom by continuous degrees of freedom, and continuous, not just continuous, but taking arbitrary real value. Okay. So as Landau emphasized that it is the symmetry of the model which is important, and he needs to kind of write down a model which preserves the symmetries. This particular model definitely preserves the important symmetry of the spin system, namely S going to minus S symmetry. Okay. The next important statement which comes from this Landau-Gisberg setup is that this feature of preserving the symmetries of the lattice model is not, although we have kind of demonstrated, okay, not demonstrated, but we kind of gave a prescription of how you go from SIs to phis following the Landau-Gisberg formulation only for Ising model. The main point that Landau-Gisberg would have made is that that this particular feature is not specific to Ising model. It is not that like only in the Ising model that you would be able to do something like this. If you consider a model which instead of having spin taking only plus minus one value, you have a m component vector and spin can take m possible values. Okay, in that case, you would have a magnetization vector which would also take m possible values. Okay, and in that case, the Landau-Gisberg action function will be written in terms of a scalar field, which itself is a vector. It's a m component vector, and there are like phi 1, phi 2, phi 3, dot, 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 up to phi m. And you write down terms which are like quadratic terms is phi dotted with phi, where this dot product is with respect to the vector on phi and not on the vector on x actually, because that is just space-time variable. Okay, and similarly, a dot product between the gradients of phi. Now this, I have deliberately not written a vector on the nabla just to kind of avoid confusion, but this dot is of course a dot product both of nab gradients as well as of phis. Okay, whatever. So I mean, one can write down terms of this kind, and with respect to expressions of this type, one can write down a Landau-Gisberg action functional, and that action functional will preserve this m component symmetry of the model that one is looking at, which is kind of generalization of Ising type model in the Landau-Gisberg formulation. And it will typo again, sorry, and it will preserve the symmetries of the original model again. Okay, so this of course is an important aspect of Landau-Gisberg formulation because of the Landau criteria that any model that you would write down has to preserve the symmetry property of the original model for which you are trying to give this description. Okay, so the entire setup is based on preserving symmetries. Okay, this is something we have already said, that we ignore higher derivative terms like grad square phi whole squared or grad phi to the fourth, and similarly higher power terms. Okay, and as we will see at some later point that like most of these are irrelevant pieces. Okay, fine. This is something we had already studied, that if you turn on a magnetic field, then you would have a term of this type to be added and your action functional will have a new piece sitting around here. Okay. So once you write down this setup in this particular form, then as I said that in this setup, the problem actually takes the form of a quantum field theory in a path integral formulation. Okay. So what we'll do is we'll kind of look at the path integral formulation quickly, and again try to get back to the Landau-Ginzburg formulation. Okay. So, but before that, is there any question here?
The
Yes.
analog of the thermodynamic limit is like taking the volume to infinity.
Yes. Yeah. So we are in some sense, if when you do quantum field theory, you have already taken a thermodynamic limit of the system because you do a full d-dimensional infinite volume computation. Okay. Okay. So let's get to the path integral discussion. This is hopefully not going to be very long. Um, just a couple of lines about quantum mechanics. So in quantum mechanics, what we do is we write down a Hamiltonian in this particular form. I should have put a hat on X also. So P is a momentum operator. X is the spatial operator coordinate. Okay, and what one does is that one can give a path integral description of quantum mechanical system by integrating over all possible paths which are appropriately weighted, starting from one from initial coordinate say xi to final coordinate f. Okay, and of course, of all possible paths, there is a classical path which is the one which is the least action path. But when you do quantum mechanics, you assign weights to various other paths which are based on this Hamiltonian, and you do a weighted sum, or in fact, you do a weighted integral uh, of that path. Okay, and that is supposed to be the quantum mechanical description of the system. One important aspect of the path integral is that although you are doing quantum mechanics, the quantities sitting inside the path integral are always classical. Okay, so because they are classical, if you want to compute say correlation functions, you don't have to order them in a particular fashion. Normally, if you want to do a correlation function, you have to order them in a causal way that uh, uh, and that kind of product you must have already studied in quantum field theory by now is called time ordered product. Okay, that you have to order the operators in such a way that from right to left uh, the way the operators are written, from right to left the time is increasing. Okay, uh, in path integral formulation, all the quantities are classical, and therefore you can write them any which way they want. When you compute them by dividing the uh, kind of time slicing the uh, path from xi to xf, then uh, any uh, operator which occurs at a particular time will naturally kind of enter in the path integral without you worrying about their ordering inside the integral. Okay, so that is one of the reasons why path integral technique is more interesting, because you don't have to worry about operator ordering at all. And of course, one can generalize this to quantum field theory setup. Okay, and it will be discussed in greater detail when you study quantum field theory 2 course. So I will not kind of spend a lot of time giving gory details of path integral for quantum field theory. Of course, there they will have to do it for various other fields, but I will concentrate only on the scalar field. So what we will do is, when you generalize this to quantum field theory, you need to replace quantum mechanical degrees of freedom, which are point particle degrees of freedom by quantum field theoretic degrees of freedom. Okay, so in quantum field theory, what happens is that the dynamical variable is not xi and pi, but phi I and pi I. Okay, pi I are the conjugate momenta corresponding to phi I. And conjugate momentum in a Lagrangian formulation is defined as the derivative of the Lagrangian with respect to the time derivative of the dynamical variables. So del L by del phi dot. Okay, that is what is pi. If you do it for phi dot for ith scalar field, then it will give you pi I. Okay, so those are the degrees of freedom which are analogs of the quantum mechanical degrees of freedom x and p. Okay, fine. So what one does is that because you have replaced x and p as by phi and pi, in the Lagrangian formulation, it would correspond to replacing x and x dot by phi and derivative of phi. Okay, ideally phi and phi dot, but uh, we we don't work with Lagrangian in quantum field theory, but we work with Lagrangian density. In other words, you of course get Lagrangian if you integrate the Lagrangian density over space, then you get integral dt times Lagrangian. But generically, it is just hold on. But generally, it is more convenient to work with Lagrangian density in field theory, and therefore the replacement rule from quantum mechanics to quantum field theory would be to replace S in the quantum mechanics, which is integral dt times L, which is the Lagrangian of the quantum mechanical degree of freedom. This is, of course, classical Lagrangian, although it is describing quantum system, which is a function of x and x dot, by action for a scalar field. Okay, and this Lagrangian density is a function of scalar field and its derivatives. Fine. So in quantum mechanics, what you do is that you integrate over all possible coordinates. Remember, you do time slicing of the path. So from xi, which is defined as t is equal to t0, or let's say t is equal to 0, and xf, which is defined as t equals capital T, okay, which is positive number. Okay, you kind of divide this time capital T minus 0, which is capital T, into n bins. Okay, so capital T by n, 2 times capital T by n, 3 times capital T by n, dot, 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 up to n times capital T by n, which is T itself. Okay, you divide the time into n such interval, take n sufficiently large, eventually to infinity, and then you say that from time t is equal to, say, alpha, not alpha, some integer times t by n, to that integer plus 1 times t by n, you look at the path going from one time slice to next time slice in any arbitrary way. Okay, and at every time slice, you integrate over possible position of the particle over entire space. Okay, so you do an integral dx. Okay, for that. Okay, but now, and that is because x itself was a dynamical variable. In quantum field theory, x is not a dynamical variable, but phi is. Okay, so therefore, when you are doing the path integral, then in your time slicing, you are actually going to integrate over all possible value that phi would take. Okay, and therefore your path integral for the scalar field would look like integral d phi exponential of I times s phi, where s phi is this expression. Okay, now this d phi is a complicated object to define. Okay, not for scalar field, it's not very complicated, but that is the object which carries the information about the quantum physics, really. Okay, because classically all the information is there in this exponential of is. Okay, so yeah, so maybe I'll just say something which is not going to be relevant for the course or most of the quantum field theory 1 and 2 courses also, is that you may have certain symmetries which are symmetries of the classical system, and those symmetries would be preserved. I mean, when you say something is a symmetry, that means it leaves the action invariant. So therefore, this entire object would be left invariant, and therefore that symmetry would be preserved by exponential of is. Okay. Now you may want to ask a question: is that symmetry preserved in quantum theory? Okay. Now, in most of the situations, that symmetry is preserved in quantum theory, but there can be circumstances in which that symmetry is not preserved. Okay. Such a phenomenon in quantum field theory is called anomaly. Okay. It is called anomaly because that is the anomalous behavior of the system. Classically, it shows symmetry. Quantum mechanically, it doesn't. Okay. The correct word should have been something else. Correct word should have been probably quantum mechanical symmetry breaking. That should have been the right word, but people use the word anomalies. Okay. Now, only way in path integral can you see that a system, classical system has a symmetry, but quantum system doesn't, is if this integration measure does not respect that symmetry. Okay, because everything else in path integral is classical. Okay, this is the only piece where you may see potential violation of a particular symmetry. If that happens, then you would say that the quantum theory is anomalous. Okay, uh, we will not get into this. It's a bit of an advanced topic, uh, but interesting because it gives very severe constraints on what are the consistent quantum field theories. If a theory is anomalous, of in particular cases, in, certain kind of anomalies are fine, but certain other kinds of anomalies are not fine. And if the theories have those kind of anomalies, you just pick up that theory and put it in the dustbin. Okay, that is the current prescription as to how to deal with the theories which are anomalous. Okay, and in fact that's not just a prescription, that is a principle of defining consistent quantum field theories. Okay, a theory which is anomalous is not renormalizable, for example. Okay, uh, but I should qualify one thing, that there are various kinds of anomalies. Anomalies involving some global symmetries is fine. Anomalies involving local symmetries is a problem, and you do not want to write down theories which are anomalous. Okay, and one of the classic thing that you will learn in particle physics course is that standard model has every potential of being anomalous, the theory. Okay, and it miraculously cancels all possible anomalies. It's first time you see is it is almost looks like a magic, but yes, it is amazingly kind of manages to cancel all potentially problematic anomaly coefficients. Okay, and so theory is very close to being in the dustbin, but survives very nicely. Okay, but like that's not the point that is going to be important for us. But all I wanted to say was that this is the one which actually carries some information about what a quantum mechanical system would uh, have, which is not there in the classical system. Okay, now the, unlike the unlike the system that we had defined earlier, so let's kind of roll back a little. Which is this. You can see that this function is e to the minus s, and therefore, and s is real. Okay, so therefore, this function would be either growing or decaying depending upon what is the value that s would take. Okay, contrast that with the partition function that you would write down in quantum field theory, and it would take a form which is like this, e to the is. Okay, and therefore, the integrand is typically oscillatory. And depending upon what values that s of phi would take, remember s of phi is again real because it is a real function of real variables. Okay, so therefore there is no hope of s being complex or something such that it can be a decaying function. Okay, so uh, so therefore it is an oscillatory function, and if s takes large values, then it can actually oscillate quite widely. Okay, so if you want to compute an integral of this kind with the oscillatory function, you need to use kind of formalism called stationary phase approximation. Okay, and use the stationary phase approximation to derive equations of motion from uh, from a partition function of this kind or path integral of this kind. Okay. Now, of course, one can do that. It's not like it's impossible to do this, but it is still not a very kind of convenient thing to do. Uh, let's put it this way: that although stationary phase approximation is reasonably well understood, the saddle point approximation is even better understood, and so therefore one feels much more comfortable using saddle point approximation than the stationary phase approximation. Okay, to put it a little differently, we would want to get rid of this I and get a minus sign there. Okay, and if we get that, we would be in much better shape. The reason why minus sign is good is because if you look at this functional is actually grad phi squared, and 5 to the fourth, and therefore the action function is actually almost positive semi-definite. Okay, because everything is mod squared quantities. Okay, or squared quantities of real variables. Okay, so therefore e to the minus s would have been a nice term to have.
So
Okay, yes,
in ordinary quantum mechanics, when we do something like path integral, we have this
yes,
instead of d phi, dx, the measure of the
yes,
integration.
yes,
That we only have one parameter to classify the paths, which is time, like from something like t1 to t2 or from
yes,
minus infinity to infinity.
yes, yes.
Here we have t and all the spatial dimensions as the parameter of the path itself.
Exactly, exactly. Yes. So that is why this d phi is a complicated object. This d phi is a value of phi at every space and time point. Okay, and you have to take a product of those for all space and all times. Okay, so if you want to define it only on a particular time slice, then for that time slice, this is a product over all spatial values. Okay, and you know that uh, spatial values are going to be continuous. Okay, so therefore this product is a kind of, if you try to explain it to mathematician, he would kind of throw his arms up saying that what kind of object is this, product, infinite product of some function. Okay, so in that sense it's a bit loosely defined thing. A lot of mathematicians are still uncomfortable, but physicists are happy.
Okay.
Yeah, I mean, for scalar field theory, I must say that, this path integral formulation has been put in much more rigorous footing by axiomatic field theorists, people like, you know, Froelich or Arthur Jaffe and, you know, James Glim and people like that, uh, Barry Simon, and they have set up this thing. But like a general setup for fermions and gauge fields and all kinds of objects hasn't been done in a very rigorous way. But any practicing quantum field theorists would say that, okay, if it works for scalar, I'm sure it works for fermion and for the gauge field and so on. I don't worry much about it. Uh, some of the details that I mentioned were like anomalies, kind of, which are some information hidden inside this integration measure. One has developed techniques for fermions and gauge fields and various other quantities as to how to extract that information out of this in a very nice way. Okay, but because we know that does not, therefore does not mean that we actually really understand this measure in a very clean way. Okay, but as a practicing physicist, you could kind of shove this mathematical subtlety under the rug and say, okay, continue working with it. Okay, so that's how it is.
So you said also that the classical symmetry is all absorbed in the S of phi factor. So like, I mean, that
Yeah.
doesn't change from going the classical theory to the quantum theory. What
Yes.
change might in anomalous cases change is the measure.
Yes.
But isn't that the intrinsic quality of the field phi itself, the measure? It has got nothing to do with the theory, like whatever action you write with.
Yes. That is true. But if you do a specific transformation, see, uh, we are talking about invariance of the integration measure under a specific transformation. Okay.
Oh, okay, all right, yeah.
So that, uh, yeah, that is not intrinsic of phi. It's a symmetry of what S would have, right? and the major may not know what symmetry S had. Major is defined once and for all, actually. Okay.
Yeah.
Okay, good. So 425 almost. Okay, where was I? Yeah. So maybe I'll kind of stop at this point. We will talk about the convergence related stuff next time. Okay. We have to do some kind of analytic continuation of this integral so that we get minus sign out here. Okay. And most of the time we'll be working in that kind of formulation. Okay. But we'll talk about it next time. Any questions?
Sir, regarding the assignment that you sent, I mean.
Yes. Yes, please.
Yeah, I was just stopping the recording.
Yeah, same here. Just hold on.